NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
James Webb will go where no other telescope has gone before.
In the vast expanse of space, just over 4 light-years away, lies a mysterious planet, much like ours. This distant cousin of our Earth can, much like our own home, host life. This is none other than Proxima B, orbiting the closest star to our Sun, Proxima Centauri. This Earth-like world has long been a subject of intrigue. We discovered it not through direct observation, but through mathematical models. However, recent findings from the James Webb Telescope have deepened the mystery and shed light on extraordinary details. Does this distant planet harbor life? If so, what would those life forms look like? Well, now we have a much clearer view since the James Webb Telescope has released a real image of Proxima B, showing us that it's unlike anything we expected. So, what do we know so far? Let's get started with today's remarkable exploration. Proxima B, the second planet Earth. At a distance of just 4.24 light-years, Proxima Centauri, the closest known star to our solar system, is part of the Alpha Centauri system, a triple-star system that includes Alpha Centauri A and Alpha Centauri B. Despite its proximity, Proxima Centauri is a faint red dwarf star that is much smaller and cooler than our Sun. This makes it challenging to observe with the naked eye. However, thanks to technological advancements in modern astronomy, Proxima Centauri has become an object of intense study, with telescopes sensitive to red and infrared wavelengths offering a closer look. While we've known about the star for over a century, since it was first identified in 1915 by Scottish astronomer Robert Innes, our understanding of its full potential, particularly in terms of its planetary system, has only begun to take shape in recent decades. So, how did we get to where we are now? Let's dig in. In the early 2000s, astronomers began focusing their attention on the subtle movements of Proxima Centauri, particularly the slight wobbles in the star's position. To the untrained eye, this may not have amounted to anything, but the experts peering across the galactic landscape knew exactly what it was. They suggested that unseen planets were orbiting the star. The gravitational forces from orbiting bodies were influencing the star's motion. As these observations intensified, it became clear that Proxima Centauri's planet, Proxima B, might be one of the most promising exoplanets in the search for life beyond our solar system. Proxima B was discovered in 2016 by astronomers at the European Southern Observatory. Interestingly, they did not technically see the planet. Instead, they used the radial velocity method to measure the minuscule shifts in the star's light spectrum as the star moved slightly in response to the gravitational tug of an orbiting planet. Ground-based telescopes like the La Silla telescope in Chile, equipped with sensitive spectrometers, provided the data, but atmospheric distortions and the faintness of Proxima Centauri itself made things difficult. Even with the remarkable discovery of Proxima B, our understanding of the planet remained incomplete. Earth-based telescopes could only provide indirect measurements, such as Proxima B's mass, orbital period, and distance from the star. But these observations couldn't offer detailed insights into the planet's atmosphere, surface conditions, or any potential for life. This is where the next frontier of exploration would come into play: space-based telescopes. For years, astronomers had hoped that future technologies would break the barriers that ground-based observations could not. Enter the James Webb Space Telescope, or JWST. With its advanced capabilities in infrared astronomy, JWST has already begun to reveal new and startling details about distant exoplanets, including Proxima B. By bypassing the interference of Earth's atmosphere, JWST offers a clearer, more detailed view of the exoplanet, allowing astronomers to probe its atmosphere, study its chemical composition, and explore whether Proxima B might possess the conditions necessary to support life. So, are we alone? Or is there someone else out there? Well, let's not rush to answer this question. First, we need to see what made it possible for us to collect the data to confirm or reject our suspicions, and why we should trust the data itself. The story of the James Webb Telescope. The James Webb Space Telescope, or JWST, is a continuation of the spirit of discovery that defined the space race of the 20th century. Ironically, the hype of space exploration is long dead. So much so that Stanley Kubrick's 1968 film, 2001, A Space Odyssey, predicted that humans would have colonized the moon and even other planets by the dawn of the 21st century. Of course, the space fever died out much before something like this could be done, but visionaries refused to give up. Space is the final frontier, and the best minds on the planet are as busy as ever, trying to explore every nook and corner. This gave us our first space telescope. Launched on April 24, 1990, the Hubble Space Telescope revolutionized our view of the universe, allowing us to observe distant galaxies, stars, and other celestial bodies with unmatched clarity. Orbiting Earth at a distance of about 547 kilometers, Hubble's position beyond the distortion of Earth's atmosphere gave it a unique advantage over ground-based telescopes, allowing for high-resolution images that revealed the cosmos in all its glory. Naturally, it has been responsible for some of the most significant discoveries in modern astronomy. One of its most iconic contributions was revealing that the universe is not only expanding, but that the expansion is accelerating. This discovery, made in the late 1990s, fundamentally altered our understanding of the cosmos and led to the identification of dark energy, a mysterious force that is driving this accelerated expansion. Hubble also provided the stunning Hubble Deep Field image in 1995, which captured thousands of galaxies in a tiny patch of sky, offering a glimpse into the vastness and complexity of the universe. Beyond these groundbreaking observations, Hubble has also been instrumental in determining the age of the universe, providing crucial data that suggests the universe is approximately 13.8 billion years old. It has contributed to our understanding of exoplanet atmospheres, observed the dynamics of galaxies, and helped clarify the processes involved in star formation. Through its observations, Hubble has enhanced our knowledge of black holes, supernovae, and the intricate workings of the universe. However, Hubble has inherent limitations. While it revolutionized our understanding of the universe, its technology is dated, and this necessitated the development of a new, more advanced observatory. Hubble primarily observes in the ultraviolet, visible, and a small portion of the near-infrared wavelengths, which, although groundbreaking, hinder its ability to peer through the thick dust clouds that often obscure star-forming regions, distant galaxies, and the centers of active galactic nuclei. Additionally, Hubble's aging instruments and hardware, dating back to the early 1990s, meant that even with periodic upgrades, some of its components were no longer state-of-the-art. The telescope's low Earth orbit, while convenient for servicing missions, also exposed it to vibrations that limited its precision. Furthermore, Hubble's relatively small 2.4-meter mirror size restricted its ability to gather light from faint and distant objects, making it difficult to study the farthest reaches of the universe. These limitations led to the creation of the JWST through a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It was named after James E. Webb, who served as the administrator of NASA from 1961 to 1968 during the Apollo program. This new and improved space telescope was finally launched on December 25, 2021. Unlike Hubble, which orbits Earth, JWST was placed at the second Lagrange point, or L2, located approximately 1.5 million kilometers from Earth. This strategic position allows JWST to maintain a stable orbit, shielded from the Sun, Earth, and the Moon, reducing interference from their light and heat. At L2, JWST can observe the universe without the distortion caused by Earth's atmosphere or the light pollution that affects ground-based telescopes. Additionally, the colder environment at L2 is crucial for the operation of JWST's highly sensitive infrared instruments, which require extreme cooling to function effectively. Most remarkably, JWST can make observations in the infrared medium. This allows the telescope to look deeper into space and time, revealing objects and phenomena that are invisible in the visible spectrum. As we observe more distant galaxies, we are essentially looking back in time, seeing them as they were billions of years ago when the universe was much younger. However, due to the expansion of the universe, the light from these distant objects has been stretched to longer wavelengths, shifting it into the infrared spectrum. This phenomenon, known as redshift, means that observing the infrared portion of the spectrum is essential for studying the early universe. JWST's infrared capabilities enable it to capture light from galaxies that Hubble could not detect, including the faintest and most distant objects from the earliest periods of cosmic history. Groundbreaking, right? But that's not all. A particularly exciting aspect of JWST is its potential to study exoplanets and their atmospheres. By observing distant worlds in the infrared, JWST can detect the chemical makeup of these atmospheres, including molecules like water vapor, methane, and carbon dioxide, which are key ingredients for life as we know it. With its unprecedented sensitivity, JWST will be able to analyze the atmospheres of exoplanets in ways that were previously impossible, offering new insights into the potential habitability of distant worlds. This capability represents a significant leap forward in the search for extraterrestrial life, as JWST can detect biosignatures that could point to the presence of life beyond our solar system. At the heart of JWST's design is its massive 6.5-meter primary mirror, composed of 18 hexagonal segments made from ultra-lightweight beryllium and coated with a thin layer of gold to optimize its infrared reflectivity. This large mirror allows JWST to collect significantly more light than Hubble, enhancing its ability to observe fainter objects with greater clarity and detail. The telescope is also equipped with a 5-layer sunshield made from a special material called Captain, which protects it from the sun's heat and keeps its instruments at the necessary low temperatures. Each layer of the sunshield reflects heat and allows JWST to remain at temperatures as low as -233 degrees Celsius. Here, its infrared sensors can operate at peak performance. The Space Telescope also hosts an impressive array of scientific instruments, including the Near-Infrared Camera, or NIR-CAM, the Near-Infrared Spectrograph, or NIR-SPEC, the Mid-Infrared Instrument, or MIRI, and the Near-Infrared Imager and Slitless Spectrograph, or NIRIS. Each instrument has a specialized function, from capturing images of star and galaxy formation to analyzing the composition of distant worlds. NIR-CAM, for example, allows astronomers to study the earliest galaxies, while MIRI extends JWST's vision into the mid-infrared spectrum, enabling detailed studies of distant galaxies and exoplanets. NIR-SPEC allows the telescope to study multiple objects simultaneously, providing insights into their chemical composition, while NIRIS ensures precise pointing and enables the study of exoplanet atmospheres. Together, these tools have given us unprecedented clarity for observing objects and phenomena that were once beyond our reach and provided new insights into the history of the universe and the conditions that might support life elsewhere. James Webb Space Telescope's findings. Located some 4.24 light-years from Earth, Proxima B is one of the most intriguing exoplanets discovered to date. It orbits within the habitable zone of Proxima Centauri, the closest star to our Sun, making it a prime candidate for the search for extraterrestrial life. Since its discovery in 2016, Proxima B has sparked considerable interest in the scientific community, particularly in the field of exoplanet research. To better understand the planet's environment, scientists turn to advanced instruments such as the James Webb Space Telescope, which launched in December 2021 and is designed to observe distant celestial objects in infrared wavelengths, offering a more detailed look at exoplanets like Proxima B. JWST's role in studying Proxima B began with its ability to observe the planet's light spectrum through a technique called light spectroscopy. This process involves analyzing the light that passes through or reflects off an exoplanet's atmosphere, which provides crucial information about its composition, temperature, and potential habitability. The telescope can capture minute details in the planet's atmospheric conditions, such as the presence of water vapor, methane, carbon dioxide, and other gases that might indicate the planet's suitability for life. Speaking of life, we already know that this planet lies within the star's habitable zone, a region where conditions may allow for the existence of liquid water on its surface, a crucial factor for life as we know it. Proxima B is slightly larger than Earth, with a mass approximately 1.17 times that of our planet. It orbits its host star every 11.2 Earth days at a distance of only 7.5 million kilometers. For comparison, Earth is approximately 149.6 million kilometers, or 93 million miles from the Sun. This distance is known as 1 astronomical unit and serves as a standard measure for distances within the solar system. In comparison, Proxima B orbits its star, Proxima Centauri, at a distance of only about 5% of the Earth-Sun distance. Normally, this would have all but obliterated the planet, if the star were anything like our Sun. But this is not the case with Proxima B. Proxima Centauri is a red dwarf star, much cooler and dimmer than the Sun. This means that despite being so close to its star, Proxima B receives a similar amount of energy as Earth, and is thus, at least in theory, inhabitable. But things are not that simple. The planet is likely tidally locked, meaning one side always faces the star while the other remains in darkness, creating stark contrasts in temperature between the two hemispheres. This phenomenon, caused by gravitational interactions between the planet and its star, creates extreme contrasts in temperature between the day and night sides. While the day side would likely experience intense heat, the night side could be incredibly cold, potentially making much of the planet inhospitable. However, the presence of a stable atmosphere could offer hope for habitability, as it might help to moderate the temperature differences by redistributing heat from the day side to the night side. This type of heat circulation could potentially create a terminator zone, or the region between the day and night sides. Here, the conditions might be more moderate, offering a better chance for life to thrive. Despite these factors, Proxima B's exposure to the radiation from its host star, Proxima Centauri, which is an active red dwarf, could present challenges. Proxima Centauri is known for emitting powerful stellar flares that could strip the planet of its atmosphere or make the surface highly irradiated. This activity raises questions about the planet's ability to retain an atmosphere or sustain life over geological timescales. Still, if Proxima B has a magnetic field and a robust atmosphere, it might shield itself from these extreme conditions. While we do not yet have direct data on Proxima B's surface composition or topography, its classification as a rocky planet hints at a terrestrial-like structure, possibly with mountains, valleys, or even oceans. So, what would the extraterrestrials look like if Proxima B turns out to be a goldmine? Revising assumptions about habitability. The discovery of Proxima B has been a turning point in our understanding of exoplanets, their potential habitability, and the quest to find life beyond Earth. The observations made by the James Webb Space Telescope and other instruments have led scientists to reconsider long-held assumptions about the likelihood of planets around red dwarf stars supporting life. For decades, it was widely believed that planets orbiting red dwarf stars were unlikely to support life. Red dwarfs, which make up approximately 70% of the stars in the Milky Way, are known for their intense stellar flares and radiation. These stars burn at a lower temperature and have much longer lifespans than stars like our Sun. While this extended lifespan could provide a stable environment for life to develop, their flares were thought to pose a serious threat to the habitability of planets in the habitable zone. However, recent findings regarding Proxima B challenge this assumption. Moreover, now we know that planets like it could be more common than previously assumed. The vast majority of stars in our galaxy are red dwarfs, and many of them have planets orbiting within their habitable zones. This opens up the possibility that there could be countless Earth-like worlds in the galaxy, many of which may be much closer than we previously thought. Proxima B's discovery has sparked a shift in how we approach the search for habitable exoplanets. While the previous focus was largely on Sun-like stars, this new understanding places red dwarf systems at the forefront of future studies. By identifying more red dwarf stars and studying their planets in greater detail, astronomers may discover that planets with the potential for habitability are far more common than we've imagined. The potential for Proxima B to harbor life, whether microbial or more complex, has profound implications for our understanding of life in the universe. This makes it a key focus for current and future astronomical research. Given its proximity, Proxima B has become a focal point for future space exploration. While current technology is not yet capable of sending probes or humans to such distant exoplanets, The advancements in space technology suggest that missions to Proxima B are within the realm of possibility. The development of next-generation propulsion systems, such as solar sails or nuclear fusion propulsion, could one day make it feasible to reach Proxima B within a human lifetime. But what can we expect to find there? For perspective, we can compare Proxima B's potential habitability to the extremophiles found on Earth and the origins of life on our planet. Proxima B is tidally locked, meaning one side always faces its host star, while the other is in constant darkness. This creates a stark temperature contrast between the two hemispheres. The side facing Proxima Centauri could experience scorching temperatures, potentially exceeding 400 degrees Celsius or 752 degrees Fahrenheit, while the dark side could plummet to freezing temperatures. Despite this, the planet may still support life under certain conditions, especially if it has an atmosphere thick enough to regulate temperature and prevent extreme conditions from being a barrier to life. Even on our own planet, extremophiles thrive in harsh, extreme environments. These organisms are found in the deep ocean, acidic hot springs, or the frozen Antarctic deserts. They provide a powerful argument for the possibility of life thriving in challenging conditions. For example, extremophilic bacteria such as Thermococcus gamma-tolerans are capable of living in extreme temperatures, and Deinococcus radiodurans can withstand extreme radiation and desiccation. More complex life forms, like tardigrades, commonly called water bears, have been found to survive in outer space, demonstrating that life can endure even in conditions that would typically destroy cellular structures, such as the vacuum and radiation of space. Tardigrades are capable of entering a state of cryptobiosis, allowing them to survive temperatures of minus 273 degrees Celsius and up to 150 degrees Celsius, intense radiation, and even space. Moreover, we know that life on Earth began in deep-sea hydrothermal vents, where extreme pressure, high temperatures, and a lack of sunlight created the ideal conditions for the first organic molecules to form. Yes, extreme conditions were, paradoxically, ideal for the kind of life that would be all but obliterated by them today on Earth. These vents, rich in chemicals like methane, sulfur, and hydrogen, could have facilitated the creation of simple compounds that evolved into more complex organic molecules. The extremophiles that live around such vents today, such as Pyrococcus furiosus, which thrives at temperatures above 100 degrees Celsius, give us a glimpse into the kinds of organisms that could have been the ancestors of life on Earth. So life can indeed find a way, even in the most hostile scenarios. Life on Proxima B might have had similar origins, with extremophilic microbes adapting to the planet's harsh conditions. If Proxima B has a subsurface ocean or is protected by a thick atmosphere, it could provide a stable environment for microbial life, similar to Earth's deep-sea vents. In this case, life could exist in the warmer, more stable regions, particularly in areas where heat from the planet's core could support life beneath the surface, much like the life around Earth's hydrothermal vents. Moreover, if Proxima B is found to have an atmosphere, it could have been shaped over millions of years by geological and volcanic activity, potentially creating a stable environment where life could take root. The presence of liquid water would increase the planet's potential for habitability, as it could allow chemical processes to occur that are necessary for life. Given the planet's close proximity to its star and the possibility of tidal locking, it's also conceivable that life could exist in a narrow, temperate zone around the boundary between the light and dark sides, where temperatures might be less extreme and liquid water could exist. Extremophiles on Earth have demonstrated that life is incredibly adaptable. If life can survive in Earth's most extreme environments, there's a good chance that Proxima B, if it possesses the necessary ingredients such as liquid water, the right chemicals, and an atmosphere, could support life too. But seeing is believing. So far, our observations have only allowed us to marvel at the planet from a distance. This dream too will come true in time though. Future of space exploration and questions. The future is already here. We're living it, or at least the makings of it. Soon, we will be able to look at the planet up close, collect samples, and even send manned missions to it. This may seem far-fetched now, but remember, the moon landing was accomplished by a species that had only 60 or so years earlier learnt to fly. Today, we're at the cusp of making similar accomplishments. For instance, The Breakthrough Starshot is an ambitious, long-term project aimed at revolutionizing interstellar travel by sending tiny, lightweight probes to the nearest star systems, most notably Alpha Centauri. Launched in 2016, the initiative is a collaboration between the Breakthrough Initiatives, a global program co-founded by Russian entrepreneur Yuri Milner, astrophysicist Stephen Hawking, and Facebook's Mark Zuckerberg, among others. The project aims to develop probes that can travel at speeds up to 15 to 20% of the speed of light and reach the Alpha Centauri system in just over 20 years. The concept behind Breakthrough Starshot centers on using light-powered star chips, which are small, flat, and highly reflective spacecraft equipped with cameras, sensors, and communication devices. These probes would be propelled by powerful lasers, which would focus immense energy onto a light sail attached to the spacecraft. As the lasers shine on the sail, they push the star chips to incredible speeds, possibly achieving velocities that are orders of magnitude faster than any spacecraft currently in operation. This approach contrasts with traditional rocket propulsion systems, which rely on physical fuel to generate thrust. Light sails, in theory, offer a much more efficient means of propulsion by using the energy from lasers or sunlight. The idea of using light for propulsion draws inspiration from theoretical studies of light sails proposed by scientists like Carl Sagan in the 70s. A key challenge for Breakthrough Starshot is the development of the technology to generate and direct such powerful lasers accurately over vast distances. The laser system, intended to focus on hundreds of square meters of sail, must overcome issues such as atmospheric distortion, ensuring that the energy reaches the spacecraft intact. Additionally, star chips must be designed to withstand the extreme conditions of space travel, such as radiation, temperature fluctuations, and high-velocity collisions with interstellar dust. The entire endeavor also involves tackling problems related to communications. Since the probes will travel at such high speeds, the time delay between sending and receiving signals will increase dramatically. As a result, transmitting information back to Earth will require innovative methods for data storage and transmission. And in most cases, communications may be one-way, meaning the probes would send data without receiving instructions from Earth after launch. While Breakthrough Starshot is still in its early phases, the project has made significant strides in research and development. By 2021, scientists had demonstrated the feasibility of light sail technology through ground-based tests and prototypes. For instance, they successfully demonstrated laser propulsion techniques with small-scale models, proving that the concept is technically sound. The project is also collaborating with various academic institutions and tech companies to refine the materials, design, and laser technology needed for this interstellar mission. The long-term implications of Breakthrough Starshot could be profound. Not only would it allow us to explore Alpha Centauri and its planets, but it could also serve as a precursor to further missions exploring other stars and their potentially habitable exoplanets. In addition to robotic probes, there is growing speculation about the possibility of sending human missions to Proxima B. While this idea is a bit farther from realization as of yet, it is not entirely out of the realm of possibility. For instance, the Mars mission is often cited as a stepping stone for human space exploration, with NASA and private companies like SpaceX actively working towards sending humans to the Red Planet. If successful, this could pave the way for future missions to more distant destinations like Proxima B, where humans could potentially study the planet's surface, atmosphere, and potential for life firsthand. The search for extraterrestrial life has traditionally focused on the detection of radio signals, based on the assumption that advanced civilizations might communicate in a way similar to humanity. However, Proxima B reminds us that life may exist in forms, and some may not even be immediately recognizable to us. This discovery challenges our assumptions and suggests that, in addition to searching for radio signals, we must consider other indicators of life. Most of all, we must make the effort to go and look for ourselves. This shift in focus could significantly broaden the scope of SETI, or the search for extraterrestrial intelligence. As humanity continues its quest to explore the cosmos, the mysteries of exoplanets like Proxima B remain at the forefront of astronomical research. Current technology offers only glimpses of the answers, and as scientists develop more sophisticated instruments, these questions may soon be answered. The promise of newer technologies, including a successor to the James Webb Space Telescope also offers an exciting prospect for answering some of these deep cosmic questions. Moreover, future projects like the Square Kilometre Array, or SKA, set to become the largest radio telescope in the world, are poised to provide unprecedented insights into the universe. This massive array, to be built across South Africa and Australia, will allow astronomers to survey the universe with incredible precision, probing deeper into the cosmos than ever before. SKA's unparalleled sensitivity and vast network of antennas will offer groundbreaking capabilities in answering some of the most fundamental questions in astronomy. These include the formation and evolution of galaxies, the role of magnetic fields in shaping cosmic structures, and, perhaps most importantly, the nature of dark energy, which remains one of the greatest mysteries in physics. As these and other future projects continue to unfold, the landscape of space exploration will undergo transformative changes. The next few decades promise to be a thrilling time for astronomy, with the potential to answer some of humanity's most profound questions. Could we be alone in the universe? Or will we find evidence of civilizations that have existed long before us? Will Proxima B turn out to be home to intelligent life? Or is it simply another dead end that has us so much excited? In any case, these questions are the driving force behind ongoing space missions and research, guiding our path toward the unknown. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.